Okay, I think we are ready to start. Hello and welcome to the last session of the day. And the first talk is on heavy quark diffusion from the lattice. It's going to be given by Viljami Leino. Viljami, you have 25 minutes and we'll have 5 minutes for questions.
Thank you. First of all, I want to thank the organizers for allowing me to give this talk. As said, I'm going to talk about the heavy quark diffusion from the lattice, and this is based on a quite recent paper we did with this awesome group of people. So just for introduction, we are studying the property of quark-gluon plasma that's generated in particle accelerators such as LHC. And here we are focusing on the zero chemical potential and the deconfined phase. And this plasma is described in terms of transport coefficients. And in this talk, we are focusing on the heavy quark momentum diffusion coefficient kappa and the related coefficients, diffusion coefficient and drag coefficient and so on. And this kappa, it's related to the experimental quantities such as nuclear modification factor, RAA, and the elliptic flow μ2, which are described by the spatial diffusion coefficient or the momentum diffusion coefficient. They are related by Einstein relation. And there are many ways you can measure these or have many different phenomenological models for the diffusion coefficient, but they have a very wide variation of results, which is why the lattice results are needed. There is a collection picture from 2018. It doesn't have our results at the moment. The μ2 is slightly larger than expected from kinetic models, but it agrees with hydrodynamic models, so the plasma is probably hydrodynamic. And well, we need the lattice perturbation, the lattice simulations to see non-perturbatively how this diffusion coefficient behaves. And here I took a picture from Mike Strickland's talk from earlier, from their recent paper where they used our results to determine the RAA. So this is one application you can do with the results we get from the lattice. So the heavy quark, when it moves in the plasma, its momentum doesn't change much in the collision with the thermal quarks. And these random kicks from these collisions then make the heavy quark undergo a Brownian motion. And it follows a Langevin equation. And then this kappa, the heavy quark diffusion coefficient, can be then related to the spatial diffusion coefficient or the drag coefficient, and also the thermalization time of the heavy quark in the plasma. Now, also we could study quarkonium in the plasma, which then satisfies these hierarchy of scales, where the M is the heavy quark mass, A is the Bohr radius, and E is binding energy, and then we have the correlation time. And in this case, instead of Langevin equation, we get a Lindblad equation, and every term here turns out to be depending on kappa and gamma. And the kappa, so by studying heavy quark diffusion coefficient on lattice, we also get the heavy quarkonium diffusion coefficient in the same time. And this can then be related to the thermal width of the quarkonium. And the gamma, which we don't study here, is the dispersive counterpart of kappa and is related to mass shift. And in this paper, they measured it from existing unquenched studies of the quarkonium, but that's out of the scope of this talk. Now, the kappa, we can derive it from the kinetic theory using this equation. And solving this will depend on the assumption that the debris mass is smaller than temperature. And you also have to expand the Gluon self-energy the first order it would be depth mass, and then you can have higher order corrections, and that will then affect what the final form of the kappa is. Alternatively, you can use Kubo formula and you get this next to leading order result with this C coefficient. We will later use this form to fit temperature dependence of our lattice results by using the C as a fit parameter. And here and everywhere else in this talk, I'm going to be assuming we are in quench theory. So the number of fermions is 0. Here's the different perturbative expectations of kappa. We can see that between leading order and next leading order, there's a huge variation. And that's why we'll need non-perturbative measurements. We also see that the assumption that the depth mass is much smaller than temperature is not very good assumption, as it gives a negative kappa, and we know from physics that the kappa should be positive. This can of course be fixed by expanding the Coulomb self-energy with the higher order or going to the next leading order, then you get positive kappa, but with huge variation. There is also a big dependence on the scale. The scale dependence enters through the depth mass, and here we just assume the next leading order EQCD result for the scale, and then later we will inspect what happens if we vary the scale with factor of 2 and use that for systematic error bars. Finally, you could measure this heavy quark diffusion coefficient from lattice using just heavy quark current correlators, but those have a very small transport peak at the 0, where you are assumed to extract this coefficient, and it's very hard to get satisfactory results that way. And that's why this heavy quark effective theory inspired Euclidean correlator was suggested by Leino et al., where we have 2 chromoelectric fields connected by Wilson lines, and then we normalize it with a Polyakov loop. And this Euclidean correlator can then be related to kappa through spectral function with the traditional spectral thermal kernel, and then taking a omega to 0 limit. This is very noisy observable in lattice, so we will have to use a multi-level algorithm, which currently is only available in quench theory, which is why I'm assuming NF0 here everywhere. This could maybe be improved with a gradient flow, which is something that is ongoing research in the community, but so far everything is with multi-level. And this has been done before, but what we have done set differently from everyone else is that we included a very wide range of temperatures, which allows us to fit the temperature dependence for the first time. Instead of inverting the spectral function, we will just have different models for the spectral function. We vary the kappa inside the spectral function, numerically integrate it, and compare it to the lattice data. Here's just the pure lattice data for anyone who's interested. Here's the list of existing lattice studies. The first 4 are with the multi-level, and this is very recent gradient flow measurement by the Bielefeld group. We used the multi-level with 4 sublattices and 2000 updates. The temperatures we range between 1.1 and 10,000. And we used the scale setting from Francis et al. Now, of course, most of the temperatures are between 1.1 and 10, and the 10,000 is just there to combine with the perturbation theory. As with very high temperature, we expect the perturbation theory to be true. Here are the raw lattice data. By itself, it's quite hard to read, so that's why we will first of all normalize it with the leading order perturbation theory result, and we will also use a 3-level improvement so that we match the leading order continuum perturbation theory to the leading order lattice perturbation theory, and that gives us very nice scaling for the lattice data. And the ZE here is lattice-only renormalization constant coming from the fact that the lattice chromoelectric field has a finite size, and in continuum the chromoelectric field is of course a point-like, so there is a lattice-only renormalization constant that we use the Leino et al. Perturbative result for. Now the question is, how much of this shape comes from the thermal effects and how much of it comes just from the running of the coupling? And for that, we plot this ratio where we take two lattice results with a factor of 2 difference in the temporal size, but the same beta, so the same lattice spacing. And doing this ratio, we then don't have any, or we don't have much of lattice artifacts since the lattice spacing is the same. And we can see that this ratio is 1 on very small separations of the electric fields, meaning there is very little thermal effects on small separations. And then we have thermal effects on the large separations. And the smaller the temperature, the bigger the thermal effects are, with the 10,000 TC being pretty much equivalent to the no thermal effects as expected. We can also see a very nice scaling if we plot everything in the physical units. And we can also see that the scaling breaks down in very small tau t, and this is probably because of systematic lattice effects. Now, again, repeating the spectral function, we have the Euclidean correlator related to spectral function, and the kappa is given by the omega to the 0 limit. One could, in theory, measure the gamma also through here. This is the quarkonium coefficient, but we don't do it at the moment. It has problems with the Cinder problems infinity, and it needs some extra normalization. On the infrared, the model we assume for the spectral function is just the simplest possible, so we invert the definition of kappa. It must hold at omega 0. This is basically the first Taylor expansion coefficient. And in the UV, we assume the perturbation theory to be true. Here's the leading order option. And then we will actually use the next to leading order option, which is given by this equation. In the UV, we will use the t equals 0 result, which is the first line here. The second line gives the logarithmically divergent full QCD result, but that diverges, so we will use that in the UV. And on the UV, we set the scale by basically setting the leading order and next to leading order spectral functions to be equal. And in infrared, we use again the EQCD result. And here is the spectral function behavior. The y-axis here is chosen so that the intercept gives the kappa. We can see that the full next to leading order spectral function replicates the kappa at the leading order. The next to leading order kappa is way bigger, but that we don't have any spectral function that would replicate that would require next to leading order spectral function. The D0 spectral function gives kappa 0, and the naive next to leading order is logarithmically divergent as said. And then we do all kinds of ansatses or models for the spectral function. The simplest possible being step ansatz, which is just we follow the infrared kappa result up till the intercept with the UV behavior, and then follow the UV behavior for the bigger omegas. And then we have a bunch of other different models. So we have these line models where we basically follow the infrared up to some point, say 0.01. And then we have like a direct triangle or a line matching to the UV behavior at some point, say 2.2. And here it's how it looks on the spectral function space for a few different choices. And also we can here see that the next leading order full spectral function actually breaks down on small temperatures, as said, because this next leading order spectral function replicates the kappa at leading order. And if you remember, the kappa at leading order is negative at small temperatures, so we can see it breaking down very nicely here. And here is the continuum limit. So of course, anything I have shown so far was on individual lattice spacings, and now we have a continuum limit. We use these three finest points, and then we assume that or estimate the systematics by including the last point. We are fixing the spatial size to be 1/48 to the cubed, because if we include more lattice sizes, we can see that the continuum extrapolation has equivalent errors to the finest lattice, so we will just use the big lattice there. The continuum limit is good as long as the tau t is bigger than 0.2 or 0.19, 0.18, depends a bit what limit you want for the chi-squared. So that's why we will only inspect separations bigger than 0.2. But of course, that's also the interesting regime. Below this, there was really no thermal effects, like I showed. And this is how the data looks if you plot it in function of tau t in the continuum limit. One would assume it to be 1 on very small separations, and it clearly is not. This means that there is an extra normalization. Clearly, the one loop renormalization coefficient ZE is not enough. And that's why we are going to just normalize everything to 1 at 0.19, as it must be 1 there. And when it's done, we can see that at the highest temperature, 10,000 Tc, the data and the next leading order spectral function and one of our models, the step model at leading order, all match perfectly with the data as long as it's normalized to 1 at 0.19. Or in this case, we normalize everything else to 0.6, but that's curious. And here is how we then extract the kappa. So what we do, we take the continuum lattice data, and well, here the ZE is the one loop normalization constant, and then we have the Cn, which then normalizes it 1 at 0.19. And then we take a model and integrate that model with running of the coupling and everything included, and then divide the data out. And if the data is then equivalent with 1, between 0.19 and 0.45, then that kappa value is equivalent. It also turns out that the step model is one extreme of our models, and the line model between 0.01 and 2.2 is the other extreme. Other models fall in between these two lines. So as long as we find the kappa for these two models, we can then use these models as the estimate for the systematic errors. And here's one extreme case, so you can see the kappa is at its maximum value for the step model, but there is still a lot of space for the line that the kappa can vary. And this is 1.1 Tc, and this is 10,000 Tc. We can see the order of the different models switches around. This happens around the 6 Tc. Which of these models gives a bigger kappa? That is. Here are our results. Focusing on first on the small temperatures regime, where all the other results are. Our results are black. We can see we agree within errors with everything else, except for the ding, but those probably have a bit underestimated errors and systematics, since those come from the current measurements, which have that very hard transport peak. But everything else here, well, all the other lattice data here is from multi-level, and we agree very well, especially with the finest or the most precise Francis data, which stated very precise measurement of 1.5 TC. And we also agree with the Alice results from 2018. And then for the whole temperature range, we can fit the temperature dependence. We see there is a clear trend of the kappa growing as the temperature is lowered. We see that the shape is very similar to the next to leading order behavior. Here the errors or the bands come from the variation of scale by a factor of 2, and also on the fit with the statistic errors. We can see our data is slightly bigger than the next leading order behavior, but otherwise it's quite close. And then we fit just using the simplest possible ansatz. This is just the next leading order function for the kappa, but we make the C as a fit parameter. And we get then the blue curve with the C equals 3.8. You can then compare this to the orange next leading result, which was like 2.6. So it is within the errors, as you can see, but it's still slightly bigger. So we have measured the kappa in a wide range of temperatures, and we, for the first time, fitted the temperature dependence. We observe that the kappa is decreasing when the T increases. This is similar to perturbation theory behavior. And in future, we are planning on measuring the gamma, which is the dispersive counterpart that affects the quarkonium physics, but you can measure it also from the quark data. We want to implement the gradient flow and then hopefully go unquenched, since everything here is NF0 and everything physical would include quarks. Then there is a recent paper by Leino et al. About 1/m corrections, which we are looking into measuring. That would be, those are given by acromomagnetic correlators. And then as a curiosity, we are also planning on extending to other operators, but those give different physics, of course. I thank you for your time.
Thank you, Viljami, for a nice talk, and thank you for finishing in time. We have a few minutes for questions. If not, let's thank Viljami again for the nice talk, and maybe we can move on to the next talk by Jacob.